So when we actually measure pH, we're measuring the acidity and the alkalinity of a solution. More specifically, we are measuring the concentration of hydrogen ions. Now, if you've ever noticed in a chemistry text or in chemistry, whenever we use the square brackets around something, we're referring to the concentration of. So this would be the concentration of hydrogen ions. That's what those symbols denote when we write it this way. Now, a couple things is you'll notice if we're measuring the concentration of hydrogen ions, well, we kind of have to look at the whole story here to really understand what this scale means, because we kind of have to think a little bit backwards, that something with a pH of 3 is very acidic versus something that's a pH of 10. You're like, well, 10 is a bigger number, so why is 10 less acidic and 3 is more acidic? Well, it has to do with the equation. And if you look at the equation on the top of the slide, pH is the negative, we're going to say inverse, the inverse log of the hydrogen ion concentration. So two things here. Making it the inverse, that's why when you get a high number, you have a low acidity. That's why when you have a low number, you have a high acidity. That's where that comes from. And by saying that it's a logarithmic relationship, remember, logarithms are based on the power of 10. And so as we go from one number on the pH scale to the next and go to the next, it's a power of 10 relationship. Okay, now remember, our exponents are based on the power of 10. So if you go from 10 to the second to 10 to the third, you're changing by the power of 10. It's 10 times 10 times 10 times 10, for however many you're going to go. So as you move from a pH of 3 to a pH of 4, okay, that's an exponential relationship. That we change by the power of 10, or pH of 5 to the pH of 7. That means we're going from 5 to 6 is 10 times, and 6 to 7 is 10 times more. And so it's 10 times 10. So there's a difference in those of 100 times, okay, the concentration of hydrogen ions. So by understanding the equation that goes into this makes it a little easier to understand the scale. We'll make more sense of it. Okay, so down here is where we're measuring the concentration of hydrogen ions. Now, before I get a little more into this, okay, I want to kind of clarify something that people commonly don't think about. And one of those being, all right, let's describe first the relationship of what we're measuring, which is the hydrogen ion concentration. So if we look at a scenario like this, where I have, again, hydrochloric acid, which then dissociates and almost completely, or does completely dissociate into hydrogen ions and chloride ions when placed in water. Now remember, our body is, okay, total body mass is plus or minus 60% water. So we release a high number of hydrogen ions with this acid, and that's why we called it a strong acid. Versus what if I have this molecule? And we'll make it somewhat simple, but let's say we have 2 carbon molecules, and around those 2 carbon molecules we've got quite a number of hydrogen atoms. Okay? And so I would ask the question, we have 2 molecules, molecule A and molecule B. So my question to you would be, given those 2 molecules, which one is more acidic? Based on now what you know about acidity and its relationship with hydrogen ions, which one's more acidic? Now, what people would commonly say is, well, B is, because I should have paused and given you time to think about it, but, okay, pause. Okay. Commonly, people would say, well, B is, because look, there's 1, 2, 3, 4, 5. There are 6 hydrogens there. There's only 1 over here. Therefore, B is more acidic than A. Okay, but what we have to remember is when we're measuring pH, we're measuring the hydrogen ion concentration, not the hydrogen atom concentration. These hydrogens have formed covalent bonds with these carbons. Therefore, this one has 2 electrons and its outer shell is full. Okay, they form some covalent bonds. They're pretty happy with what they are. These are not hydrogen ions. These are hydrogens. So B is not acidic because it doesn't release hydrogen ions. A is acidic because it does. So that's an important thing to understand, because people will see these big long chains of carbon and all this hydrogen, and they'll say, oh, look how acidic that is. No, it's not, because those are hydrogen atoms, and they're forming covalent bonds, or they're forming bonds with other atoms. They're not hydrogen ions. Okay, so another important thing we want to understand is we want to look at it from the standpoint of what is a hydrogen ion? And so my question to you would be, okay, and if you have a piece of scratch paper, do this for me. I want you to draw a hydrogen ion. Okay, this is your little exercise to do, okay, no matter when you're listening to this. Okay, for me, okay, hit pause, whatever you need. Draw a hydrogen ion. How would you represent that? Okay, so let's do this, okay. Let's draw a hydrogen atom first. So hydrogen being number 1 on the periodic table, that means at the nucleus I have 1 proton. And if it's a neutrally charged atom, if I have 1 proton surrounding that nucleus, I better have 1 electron, which has a negative charge. So in my most common isotope of hydrogen that we find, okay, 99% of the time, okay, we have 1 positive charge, 1 negative charge, and that forms hydrogen. So what I want to do from that is, okay, now make it a hydrogen ion. Now it still has to be hydrogen. So what can't you change? Well, I can't change the number of protons. Well, when I change something to become an ion, I change the number of electrons to do that. So what would I do to the number of electrons to make it then a cation, a positively charged hydrogen ion? What would I do? Well, what this symbolism means is it has to be hydrogen. Okay, that's why we have the chemical symbol there. And the pluses have to outnumber the minuses by 1. Well, how are we going to do that? Well, the pluses have to outweigh the minuses by 1. So to do that, what would I do? I would get rid of the electron. Now do I have hydrogen? Yep, it's got 1 proton. And do I have the pluses outweighing the minuses by 1? I do, because I have 1 of these, I have none of these. So really, now let's make the statement, what's a hydrogen ion? A hydrogen ion is yes it is, it's a proton. That's what it is. So when we're measuring the pH, we are measuring the hydrogen ion concentration. We're measuring the number of hydrogen ions released, but we're measuring, or the concentration of those, okay, we're measuring the number of protons released. Sounds kind of dumb, okay? So when somebody says, hey, that's a proton donor, okay, it's releasing, yeah, it's an acid, okay, because it's releasing that hydrogen ion. And so now you can look at the pH scale and you can say, okay, here's my concentration of hydrogen ions. We've circled that. I have 10 to the 0, remember that's 1, okay? And this is how many moles per liter, how many moles of hydrogen ions. So this would be 1 mole per liter. This would be -1, so it would be 0.1 moles. 0.001, 0.0001, 0.00, you get the idea. So actually the concentration of hydrogen ions is getting smaller. Therefore it's becoming less acidic. Now notice the concentration, 10 to the -12, 10 to the -11. Notice what that corresponds with. If you take that exponent and take off the negative sign, notice that's the pH. So a pH of hydrogen ion concentration of 10 to the -6 is a pH of 6. 10 to the -5 is a pH of 5. 10 to the -4 is a pH of 4. So notice my hydrogen ion concentration is getting greater and my pH is getting lower on the pH scale. So basically 7 is neutral. Now 7.1, okay, would be alkaline. Okay, 6.9 would be acidic. 7 is neutral. 10 to the -7, okay, it's neutral. And notice at 7, the reason it's neutral is because I have 10 to the -7th of hydrogen ions and also have 10 to the -7th of hydroxide ions. So the acid and base makes that neutral. So you can see that relationship. But the lower the pH scale goes, the more acidic. The higher the pH scale goes, the more alkaline it is. Now, remember we said that this was a logarithmic relationship. And we said, notice, logarithms are based on the power of 10, so are exponents. So as I go from 10 to the -3 to 10 to the -4, so my pH is going from 3 to 4. How much is my hydrogen ion concentration changing? 10 times. Now as it goes from 3 to 4, it's becoming more alkaline. Okay, so let's kind of put a couple of examples here. So if I said you have 2 solutions, and one has a pH of 3 and one has a pH of 4, and I would say which one's more acidic? That would be 3. How much more acidic? 10 times more acidic because it has 10 times more hydrogen ions in a pH of 3 than in a pH of 4. If I said you had a solution, one was a pH of 5 and one was a pH of 3, which one's more acidic? The 3. How much more acidic? 10 times 10, not 2 times 10. Each step is tenfold. So 10 times 10, so it's 100 times more acidic. And so really, as we move from one pH number to the next, the change in the hydrogen ion concentration is significant. And so even in our body, and we're going to talk about where we are on this pH scale, because you, okay, are actually a little bit alkaline when it comes to your blood pH. Now some of, like urine can fluctuate a little bit, okay? The rest of your fluids don't, and there's a reason they don't, okay? And that we will discuss in detail in the next unit, but I'll introduce it here. But the relationship there is how much does the pH change as you go from one pH, one number on the pH scale to the next. So 7 is neutral, anything above that, okay, alkaline, okay, anything below that, acidic. What does it correspond with? What are we measuring? The hydrogen ion concentration. What is a hydrogen ion? Hydrogen ion, okay, is a proton. So again, anything less than 7 is acidic. There's more hydrogen ions than hydroxides. Anything greater than that, there's more hydroxides than hydrogens. Okay, 7, yep, that's when it's equal. Now, within our body, there's with a bunch of different solutions, liquids in our body have different pHs. We're fairly consistent. Probably the one that we're going to beat you up with the most, okay, is going to be this number, or this range of numbers, the blood pH, 7.35 to 7.45. And in your body, there are fluids that, or better said, things that we measure that are in very tightly held normal ranges. So when you go to the physician and they draw blood and they want to measure certain things, they want to measure what your sodium level is and what your potassium level is, those electrolytes we discussed, or they want to measure your pH. There are very strict ranges that your body keeps you in. And if you go above that, yeah, you're sick. Okay? If you're below that, yeah, you're sick. And it doesn't take much of a change before you're real sick. And so our pH, specifically our blood pH, okay, now, and that's something important because actually today I was listening, I was at the gym and there was a story on one of the news programs that was talking about a manufacturer, and it didn't give any details, one of those little scrolling headlines down at the bottom, where it pointed out the fact there was a manufacturer bringing out contact lenses that could measure your blood glucose or monitor your blood glucose. And now, first of all, it's not true because your contact lens doesn't touch blood. But to help people understand what this contact lens does, okay, the contact lens isn't monitoring your blood sugar because it's not sampling blood. But it is monitoring, okay, your lacrimal fluid, your tears. Well, your fluids have very similar stuff in them, sometimes a little bit more, sometimes a little bit less. So it's actually when somebody's blood sugar is out of control, it's not just their blood that's out of control. Yes, that's what we measure, and that's what we say, your blood sugar is out of control. But let's say their blood sugar is high. Let's say their blood sugar is 600, 700. Well, yeah, their blood sugar is high, but so are their other fluids. Okay? The reason that they have trouble with their vision is because the fluids in their eye are high as well. The reason they can measure it on, for example, their tears is because their blood sugar, their body sugar is high. It's just we measure it in the blood. And so frequently, that's why we refer to a lot of things in terms of, okay, what is the blood concentration of this and of this? Because it's the easiest one to get. Nobody wants to say, okay, well, let's measure your lacrimal sodium level, your tears, okay, or your synovial this, or your CSF that, or we do that. We do those things, but they're not easy fluids to get, and to get in large amounts like the blood is. We stick a needle in a vein, and that's where we sample it. So we frequently sample the blood, but all of the fluids of your body contain those similar things that we look for. So that's important to understand. So what you can see, and this makes sense, is on our scale, gastric fluid. Okay, we're going to use that for digestion. And all of the hydrogen ions that we pump into the opening or the lumen of the stomach makes that a very acidic environment to help break down some of those nutrients, especially break down proteins. Lemon juice, okay, so gastric fluids anywhere from about 1.2 to 3. Lemon juice, 2 to 3. Vinegar, okay, notice this is kind of interesting. This will be represented a little bit or reflected in the next concept we discussed. Notice how acidic soft drinks are. If you measure the pH of Sprite, the pH of Coke, yeah, you're hanging right around 2.6 to 3, somewhere in that range. Even a little more acidic than what even orange juice is. Okay, if you'll notice, some of the fluids of the body that, for example, vaginal fluid actually has, for females, it has a protective mechanism, makes the vaginal environment a little more acidic, less likely for pathogens to be able to colonize, so it does have that advantage. Tomato juice, coffee's about 5. Now notice urine. Urine varies between 4 and 8, about 4.5 and 8. So it depends on what your body's trying to do. If you are a little bit, quote unquote, too acidic, well then your urine, in an effort to dump that acidity, your urine's going to become acidic. In other words, if you are accumulating a few too many hydrogen ions, which is normal, then your body's going to dump a few. Or where is it going to dump it? Well, out the urine. Or if you're not quite acidic enough, you're a little more on the high side of the normal body pH. Well, your body's going to save hydrogen ions, so it's not going to release them into your urine. That's not saving. Okay, that's dumping. And so you end up more on the high side. So if you want to be more acidic, then your urine becomes more alkaline. If you want to be more alkaline, then your urine becomes more acidic. And that'll become very evident when we cover that system of the body. Okay, so you can see some of the others that we have within our body. They're bile, our pancreatic fluid, full of bicarbonate. Bile is also very alkaline, helps us in our digestive process. Okay, you can kind of see where some of the normal fluids of our bodies are.